There's the ding. We're live. Number 3, let me cut and paste it. So cut, because this is a big diagram, and I know I'm going to need more room than I left you here. That means it's a good question if I need more room. So I said to you, Dylan, I'm going to target the 5 kilogram mass, find everything, and I think the key is if I can find tension from over here somehow, I know that's tension over here. I might be able to work my way backwards. I think. So let's see. Let's label the heck out of this. First of all, what are the forces acting on this? I have big mg, normal force, friction. No, it says frictionless, and I have tension. Here I have, I'll call it little mg or m2g. Normal force number 2, I'll call this normal force number 1 back here. And tension. I said because I'm missing a mass, I'm really going to focus on the one mass that I do know. Hey, that's the right-hand mass, the 5 kilogram. We're going to break gravity up into its components. We're going to break gravity up into mg perpendicular and mg parallel. And we're going to use Cole's law, which was 2 lines as sine, as our, and that means perpendicular is going to be cos. I passed that on to my block A's, and I've even named it after you. It shall be named thus for the remainder of my teaching. Yes? Oh. And 90-degree angle right there. Okay. Let's just look only at the right-hand mass, because we don't know both. Who's winning? It's a trick question. It's a tie. What that means, can you see which 2 forces are equal to each other in this diagram? Can you see it? Tension is equal to what? No, it can't be equal to 0, otherwise this would be sliding. Tension is equal to what? There are 2 forces, because it's at rest, there are 2 forces that are imbalanced. And maybe I'm asking you to make 3 steps in your head, when it may be a bit much. Show, what do you see it? Nico, my friend, this and this got to be the same, otherwise it would have to be sliding up or down the hill. And because those are the only 2 forces on that mass that are in the same direction as the ramp. The fact that it's at rest, they must be equal to each other because they're in opposite directions. Yes. They cancel each other out. When you add them together, you're going to get 0. But I think what I can say is, and show is correct, I think I can say in this case, tension equals m2g parallel. I'll call it m2 and m2 so I'm not confused. And Cole has conveniently told us 2 lines as sine. Tension is actually m2g sine 50. He already has, thanks. Tension is m2g sine 50. Now, how does that help me, Dylan? Pause. Yump. Let's go to the left hand, the mystery mass. This would be big M G perpendicular, and this would be big M G parallel. Ooh, I can write an equation for the parallel forces on the left side too. On the left-hand side, what does tension equal? Can you see it? I think on the left-hand side, tension equals big M, little g, sine 30. But what else is tension equal to? I think what I can now do, Dylan, is take this and replace it. This is my actual equation. As it turns out, I'm going to get m2 g sine 50 equals big M g sine 30. Dylan, is this okay so far? Yeah. By the way, this is a tough question. I would consider this, I mean, not an A+, definitely an A-, like I would expect my top, 20% of the kids to get this. I would expect most of my kids to follow my explanation right now, but I even expect a few kids to be going, drool. But yeah, this is a tough question. Solving for M. But now I can, because do I know M2? Check. In fact, as it turns out, Dylan, this is another strange question where I guess this setup would work on Mars or on the moon just fine. Kind of cool. Do I know M2? Yes. Do I know sine 50? In fact, you know what? Let's get the big M by itself. I think it's going to be mass 2 sine 50 divided by sine 30. See if I'm right. Mass 2, 5 sine 50 divided by sine 30. 7.66. What's the answer say? Woohoo! There you go. So my strategy generally, Dylan, and I think there is one on your test, and there's several in your review, if they don't give me a mass, go target the mass that you do know, find all of the forces you can from that mass. Usually it's a tension or an acceleration. One of those you can flip over to the other mass and write a one mass force equation for the mystery mass. And if you're good, hopefully there will only be an M that you don't know. Is that all right? Anybody want me to do number 8? Okay. 8 is nasty too. 8 is... Okay. Number 8 is tougher than I would ask on the written, although I have seen this on the multiple choice as a nasty multiple choice. And in fact, I think on one of my exams, there's something similar to this as the nasty multiple choice question. So it's fair game, Courtney, but not for 7 marks. Not for a big, huge written question. Although, kind of should be. Anyways, let's clip that one too, because I'm going to need to write on here. All right. It says for the system below, find A, the direction of motion. Vlad, I'm pretty sure because the right-hand mass is both heavier and steeper, it's sliding to the right. But I could crunch the numbers. We did practice that last lesson. We said, actually, what you're looking at is the coefficient. You just kind of look at the friction forces and the gravity forces and see which one's bigger. But I think here, heavier mass on a steeper hill is going to be pulling down more. So direction of motion to the right. And you know what? Even if I guess wrong, how will I know when I do B if I get a negative acceleration? And it's a quick fix. I did show you how you can calculate ahead of time last lesson. We looked at how would you determine the direction the system moves, whichever is larger between, yeah, whatever. It's to the right, and I'm in a rush. So B, the acceleration. Oh, and then once I find the acceleration, we're going to assume it starts from rest. They want me to find the speed. A equals whatever, T equals 3, VI equals 0, find VF. That shouldn't be too much of a problem. Definitely you can expect on your test, I'm going to give you at least one question on the written where not only, Rob, do I say find the acceleration, I'm going to ask you to do something with it. Find a distance, find a velocity, find a time, something. A nice way to really review the entire year so far in one question. Hey, I like that. So what are the forces acting? Get the obvious ones we have. Yoink. M1G. Normal force number 1. Friction force number 1. Tension. Yes? M2G. Normal force number 2. Which way would friction be for this guy? Down the ramp or up the ramp? It's sliding down, so I'm going to put tension here, and then right here I'll put friction just so it stands out. It's, otherwise, if I put it right on my diagram, they're going to overlap and it's messy. Ugh. Oh, components, because we got slanties. So let's break this up into M1G perpendicular, M1G parallel. M2G perpendicular, and M2G parallel. So far, so good, Vlad? Yep. Who's winning? M2G parallel. Yes. So anything that ends up pointing this way. So it's going to be M2G parallel is a winner. Then I guess I got minus tension and minus friction force number 2. I didn't put a 2 on that one. I should have. They're both losers. Plus tension. Yay, tension cancels. Minus friction, come on, friction. Come on, pen. Doesn't want to work right there. I got a dead spot on my screen right there, I think. Friction force number 1. Oh, and also minus M1G parallel. Yes? I almost missed that. That equals M1 plus M2A. Okay? I was going to say this. I would consider this fair game for multiple choice. Yay. So far, so good. So far, so good. M2G parallel, that's going to be M2G, 2 lines is sine, and M2 goes with the 45-degree angle, minus friction is what times what? I don't know the normal force. Oh, it's going to be mu M2G perpendicular, which is going to be cosine, and if you felt really confident and did that substitution right now, I wouldn't really have a problem, although I wouldn't do that on a test. Show extra work on a test, yes? Minus friction force number 1, that's going to be M1G perpendicular times mu. Almost forgot the mu. Minus M1G sine 40. How would I get the A by itself, Vlad?
Divide.
Do you mind? Can I do that right now? I'm going to go equals A, and I'm going to go divided by M1 plus M2. Can you take it from here, or do you want me to keep going?
I had this before.
Oh, you had this before?
Yeah.
Okay, so you did all this. It's okay. I see about 8 people kind of copying this out. This is good. All right. M2G sine 45 minus mu M2G cos 45, because Cole has given us that convenient little memory trick, minus mu M1G, it's perpendicular, it's cos, but not 45, it's 40, minus M1G sine 40, all divided by 6 plus 5. All right. How big is M2? 6. How big is M1? 5. Because I'm running out of room and pressed for time, I'm going to be really, really bad. I'm going to go 6, 6, 5, 5. What was mu? 0.1. I'm going to go 0.1. 0.1, and I'm going to start crunching numbers now. So you got this line, so I'm guessing it was a calculator error, or maybe the answer key is wrong. It's possible. Bracket 6 times 9.8 times sine 45, close that off, minus 0.1 times 6 times 9.8 cos 45, close that off, minus 0.1 times 5 times 9.8 times cos 40 minus, move over, 5 times 9.8 times sine 40, close off the sine, close off the top, divided by 11. Is the acceleration 0.197? Is it? Woohoo! 0.2? Oh, I'd go 0.197. And then V final equals V initial plus AT. If I go that times 3, it's going to be moving 0.592 meters per second after 3 seconds. Was it 3 seconds? I think it was. So Vlad, if you had all that, I'm assuming a calculator error. Nice job. Yeah.
What proof do we have to have for direction of motion again? Can we just say that it's bigger mass and short rope?
It has nothing to do with the length of the rope. Okay. It's going to be, it's far more complicated than that. Generally, the bigger mass wins, but if you have a bigger mass on a shallower hill and a heavier mass on a lighter mass on a steeper hill, gravity's pulling down more. What I would say is make an educated, honestly, make an educated guess, and if you get a negative acceleration, you know you guessed wrong, go back and just quickly redo make your winners, losers, losers, winners. The only one that's going to change is friction might completely flip directions, because if that had been the winner, now I have friction pointing the wrong way and pointing the wrong way. Okay, that I got to change. But that's still not too bad a change. I got to be honest, it's pretty quick. And I can probably still do it by making pluses and minuses in my equation. Okay? Any other questions? So I have a take-home quiz for you, and we're going to finish off the unit today. You guys are one class ahead of my block A's. We'll talk about when the test is a bit later. Classic questions. I called this Lesson 8, Various Two-Dimensional Force Problems. Number 1 is the lawnmower problem. I like this question, I like this question, I like this question, I like this question, I like this question. We call it the lawnmower problem because we're talking about when you push a lawnmower. When you push a lawnmower, the handle is always angled to the earth, but the lawnmower goes horizontally forwards. That means when you're pushing along the handle, what you're really doing is you're pushing both down and forwards at the same time. So the definition is a problem where we have vertical force components other than the normal force and weight, mg. So in a problem like this, the normal force is not going to be equal to mg, or if you're on a ramp, the normal force won't be equal to mg cos. You're going to have to do some thinking. Example 1. So here we have, instead of a lawnmower with wheels, I wanted to include some friction. So we're sliding something along the floor, but instead of pushing straight horizontally, we're being dumb. We're pushing down and horizontally. We're pushing with 200 newtons at a 20-degree angle. It says find the normal force, friction, and the acceleration. Okay. Any thoughts on how I'm going to start off? I'm going to label. What are the forces acting on this 50-kilogram box? Hit the obvious ones. So, and I'm going to put the gravity actually right next to the G because I'm going to need some room. What else? Normal force. Hold off on that for a second. We're going to come back to it because here's what I don't want to do. Look, 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 look. I'm not going to go, oh, it's the same size as gravity. I don't think it is because I see other vertical stuff going on there even though I haven't done the components. What else? Friction, which way? Left. Let's do that. And then we have the applied force here. Now, it's kind of weird because we have it coming into the diagram. If you wanted to, you could redraw the arrow like that. I'm not gonna. I'm gonna live with the arrow where it is, because this isn't an actual free body. I'm labeling my forces. But what's weird about the applied force, Nathaniel? There's an angle. Any suggestions on what we should do? Darn right. We're going to break it up into, I'll call it, how about Fy for vertical and Fx for horizontal. We haven't drawn the normal force yet. We're going to in just a second. Is this block sinking into the ground like quicksand? Is it lifting into the air like Superman? So my vertical forces have to be the same, canceling each other out. Can you see I have two forces downwards though? Mg plus what else? Fy. Fyi, look at Fy, right? Which means I think the normal force is going to cancel out gravity and cancel out Fy. It's going to be pretty big. If I asked you to draw a free body diagram, I would look for a larger normal force. Or if instead of pushing down, if we were tugging upwards, I would look for a smaller normal force. Because when you're tugging upwards, you'd be taking care of some of gravity's force. What is the first thing? What do they want me to find here first, Joe? Okay, let's do that. Let's call that part A. I think what they're really saying is write a vertical force equation. So can you see, because vertically I know everything's in balance, it's not flying into the air, it's not sinking into the ground. Can you see what forces are equal to each other? It's going to be winner minus loser equals 0 because it's not accelerating vertically, but maybe we can go with a shortcut and go straight to an actual balanced equation. What equals what here vertically? Can you see it? Can you see it? Sebastian?
Fn equals Fy plus Fg.
Normal force equals the vertical component plus gravity. If there was a scale underneath this box, the scale would be reading heavier than just the box. Mg, no problem, 50 times 9. Oh, Fy. Trig. Hypotenuse. Fy, opposite, adjacent, or hypotenuse. Oh, it's going to be sine. In fact, I think here we can use our sine as y, but I wouldn't fall back on that too much because that's not always going to work in this unit, because what if your force is at a slant and the ground is at a slant, but a different slant? Okay, then you got to be way more careful. But I'm pretty sure I would end up over here going sine of 20 equals opposite over applied. I think Fy is going to be the applied force times the sine of 20, which means now I can plug stuff in. Normal force is going to be 200 sine 20 plus 50, 9.8. Which is what? Okay. 200 sine 20 plus 50 sine, not sine, Mr. Dewick. 9, how about times 9.8? 558? Oh, I thought you said 58. 558.4, 558 newtons, because it's a force. So Cole, if we weren't pushing down, normally, no pun intended, normally that's your normal force, mg, but we're pushing down, so normal force got bigger or smaller? Bigger. Friction is what times what? What happened to friction? Bigger or smaller or the same? Friction is what times what? Mu times the normal force. What happened to the normal force? So what happened to friction? Bigger. This is a dumb way. This is why you don't push down when you're trying to slide something across the floor. In fact, if you're really clever, you lift up as you're trying to slide something across the floor, because that would decrease the normal force and decrease friction, and then now it's easier to slide. In fact, if you lift it all the way off the ground, friction is now 0, because normal force is now 0. But then sometimes that's, if it's really, really heavy, sometimes there's a somewhere in between is the better way to go, between lifting it completely off the ground and sliding it straight sideways. Most people you find somewhere in the middle if you're not going to scuff the floor. So what's B want me to find? Oh, that didn't work. Let's try that again, Mr. Duke. I didn't want to go red and black. B. Friction, which is mu times the normal force, which conveniently I just found. What's mu? 0.1 times 558. I don't even think I need a calculator for that. I think multiplying by 0.1, doesn't that just divide by 10? It's 55.8 newtons. All right. What's C want me to find? Who's winning? That's a tricky one. First of all, it can't be the applied force, because the applied force is not in the same direction that it's moving. I'm pretty sure it's moving to the right, and the applied force is pointing slanty. What? Who's winning? Fx. See it? Oh, who's losing? Friction. My equation now is going to be winner minus loser equals ma. Oh, Fx. Well, Adjacent, which trig function? Not sure? Okay. I think it's going to be cos of 20 equals adjacent over hypotenuse. How would you get the fx by itself, Cole? I think what you're saying is this is going to be the applied cos 20 minus. Now, if I hadn't found friction already, I would say friction is what times what, mu times the normal force. I don't know the normal force, and I would walk through step A and step B somewhere. Well, probably in my work. I would probably draw a little arrow, a little note, or whatever. But did we already find normal force? Yeah. And did we use that already to find friction? Well, heck, let's just plug it in, 55.8. Equals the acceleration and divide by mass to get the acceleration by itself. Acceleration is going to be, what was F applied, 200? Cos 20 minus 55.8, all divided by, what was the mass? 50. $200 cos 20 minus 55.84. I'll even use the 84 from my previous answer. Divided by 50. You get an acceleration of 2.64 meters per second squared?
Yeah.
Woohoo! Could I now ask you to do something if I told you we started at rest? Could you find V final or time or distance if I gave you some information? Yeah! Sure. Totally. By the way, what if I told you that we were pushing and it wasn't moving? What would the acceleration be? 0, and you could work your way backwards and maybe even find the coefficient of friction that was required to keep this thing from moving. There's all sorts of different ways, mix and match. It starts out with the same procedure, but Dylan, what we're saying this year is going forwards or going backwards. I can either say, here's the information, find the answer, or I can say, here's the answer, here's most of the information, find the missing piece of information, right? Ooh, example 2. Says, write force equations for a mass on the ramp as shown below. The force F represents a person pushing down on the mass. The system is at rest. I think I'm going to underline this word here, at rest. I think it's important. In fact, I know it is. All right. What are the forces acting on this block? Get the obvious ones. Darn right, gravity. Friction? They wrote a mu there. I think that's their way of saying, yeah. Which way does this block want to slide? So which way do you think friction is? Okay. Now there is a normal force. Normally, no pun intended, don't write this down. Normally I would say, here's mg perpendicular, and the normal force cancels it out. But is there, can you see in your diagram, another force in that there same direction there? I think the normal force is going to have to be this big plus however big that is. It's got to cancel both of those out. Otherwise, this would have to be sinking into the ramp like quicksand. So I'm going to draw a longer normal force like that. And then I'm going to break gravity up into its components of mg perpendicular and mg parallel. Now this is not asking us to solve, it's just saying write the force equations. Okay, let's write the, I'll call it the vertical force equation, the perpendicular force equations. Since we're at rest vertically, perpendicularly, what equals what? What forces are canceling each other out? Can you see it? Because I know the acceleration is 0, so this is going to be an equilibrium equation. I can just think and say. Parallels, okay. If we're talking about along the ramp, so not perpendicularly, but parallelly, grade in what? I totally agree that this is true. Yep. Why? At rest. Okay. There's a second equation, because I would say friction is what times what, and you would answer mu times the normal force, and I would say, I don't know the normal force. Oh, but look, look, look. Ooh. There's your second equation. Yeah, let's even call it F applied since you used that wonderful word. Yeah. Yeah. And now I could tackle this. I mean, I'd need the actual data, but sure. And in fact, I would almost argue this isn't that much tougher. It's longer. Oh, and I had to think. I saw you really thinking, and okay, let's look. Yeah, but go back to Newton's laws and first principles. You know what? If it's not accelerating off the ramp or sinking into the ramp, that means the perpendicular forces got to cancel out. The net perpendicular force has to be 0. Winner minus loser. It's a tie. Cool. Number 2. While this is nerdily cool, I'm actually going to pass. So the boat problem, we're going to come back and tackle it another day.
See it on the test?
No. Number 3 is the static equilibrium problem. We're going to do an entire unit on static equilibrium. And so number 3, hopefully 3 units from now, we're going to be looking at static equilibrium and rotational equilibrium. I didn't fit it in last year. I'm hoping I can fit it in this year because it's nerdily delicious. So number 3, I'm also going to say, hang off. We're going to come back to it another day. So it won't be on the test either. Pardon me? What was that? You can, yeah, you can cross them out. They're going to show. I actually am going to be using these same questions later on in a different handout, like a month and a half from now. Number 4, the accelerometer problem. This is nice just because it's good nerdy thinking. So I want you to watch something. So here's what we're looking at. An object in an accelerated system tends to move opposite to the direction due to its inertia. Its mass wants to resist the acceleration, Newton's first law. Objects want to remain at rest or go in a straight line at a steady speed. So example 7 says, find the acceleration of the rail car that will keep the pendulum at this angle. You okay there, Vlad?
Yeah.
You sure?
Yeah.
Someone making fun of you back there?
Sure.
I'll get him. Bonson Park, 3 o'clock. If I'm not there, start without me. Example 7 says, find the acceleration of the rail car that will keep the pendulum at this angle. We're not going to do the crunching of the numbers. I'm not going to give you one quite like this on the test. What I do want you to look at is example 8. Example 8. If the rail car is lowered down the ramp at a constant speed, which diagram shows the correct position of the pendulum? A, B, C, or D? And convince me. Okay, sure, let's vote. Who says A? Who says B? Who says C? Who says D? So it's split between A and B. How could we answer this? Constant speed, so your net acceleration is 0. What does that mean? Sebastian, what were you saying?
The example you just showed us, that just leveled out. When you're at a constant speed, the ball leveled out. When you're accelerating.
If I'm at a constant speed, what's my acceleration?
0.
0. So, here's my ramp. Here's the ball. Okay? If we tilted this whole classroom, wouldn't it still be pointing straight down? It wouldn't be going like that, would it? So I don't think A is right. Like I think B is, I think it would hang straight down no matter what. As long as you're at a constant speed and no acceleration, that means the net force acting on it is 0. That means the only two forces acting on it are gravity and tension. Constant speed. Constant speed, B is right. Now, that's a rope. It's going to hang, gravity, we're going to pull it straight down. Now, if we start accelerating down the ramp, if we let this speed up, what would be the correct picture? A, B, C, or D? That's a better question. I don't think it would be D. It's not going to suddenly go shooting forward. I don't think it's going to be B. I think when you accelerate, it's going to, inertia is going to pull it back. The real question is it going to get pulled back to A or get pulled back to C? I think it's going to get pulled back to A. I think A is the equilibrium point. Meanwhile, what's your homework? We are done the unit. Okay? Questions you want to try. Number 1, now when they're talking about a lawnmower, they're assuming you're pushing down the handle like that, at an angle. So for number 1, pushed. Number 2, now you're pulling, so now they're talking about a force in that direction. Because sometimes you do pull a lawnmower too. So try number 2. 3 and 4 are really overkill. 5 and 6 are really overkill. Nah. Start the unit review. Give me 1 second, I'll tell you when your test is, I think. So for those of you watching at home, I think the test is going to be Monday the 19th. Before I turn you loose, quick video.